Welcome to the Hughes Communications Lab of the University of Maryland at College Park. I'm Alejandra Mercado. I'm Associate Director for the Masters in Telecommunications program at the University of Maryland at College Park. I'm also an instructor, a mentor, an administrator, and a lab coach. The Hughes Lab provides hands-on experience where students learn to work with the ETIS B210 software-defined radio, as well as the GNU Radio Companion, which is a front end to the GNU Radio libraries for digital communications and signal processing. Today we're going to see the eye diagram with different implementations of a signal. We're going to use arrays, cosine, pulse shaping on our bit signals. We're going to see root raised cosine pulse shaping. We're going to add noise to the signal and see how that affects the eye diagram. And we're also going to artificially create multipath intersymbol interference, like channel multipath intersymbol interference. So let's start. This is a very quick review of what we see before. We know that that in an ideal situation, you would transmit, for example, binary phase shift keying with bipolar non-return to zero signaling. It would be represented in perfect rectangles, but that's not ideal. That's not realizable. What is realizable is when you pulse shape and smooth out the signal. The problem with arbitrary pulse shaping is that you may incur intersymbol interference, and that's when we saw that raised cosine or raised sine is a situation where you don't have intersymbol interference. Okay, so we want a smooth shape that does not interfere with past symbols, and we know that one pulse shaping that satisfies this is the raised cosine filter. Remember, in the time domain, it sort of looks like a sinc times a cosine, and in the frequency domain, it looks like a smoothed out rectangle. The question is, we know we want to do this. How do we implement this pulse shaping? And that's what we're going to see today, and what can go wrong. So what we're going to be doing is we're going to be asking GNU Radio Companion to generate random bits. We're going to map the bits. Every 0 is going to be represented by a -1, and every 1 is going to be represented by a +1. Then the sample points that are coming out, -1 and +1, we're going to be feeding through an interpolating filter. So the 0s and 1s gets turned into -1s and 1s, and the interpolating filter does two things. Each bit is replaced with 30 samples, and then that signal of samples is convolved or filtered with a raised cosine impulse response. So let's look inside of the interpolating FIR filter that we're going to be using. The first thing that happens is that each bit, so either 1 or -1, 1, -1, -1, gets turned into 30 samples. So this one is these 30 samples, and this -1 is these 30 samples, and this one is these 30 samples. I couldn't fit all 5 bits into this. Then the interpolating FIR filter will convolve this. It will act just like an FIR filter with an impulse response of a raised cosine. All right. Therefore, the output will be the convolution of the impulse response of the raised cosine and the 30 samples per bit that is coming into the filter. So here you can sort of see that the 1 gets mapped into this positive bump, and the -1 gets mapped into this negative bump, and this 1 gets mapped into this positive bump. Okay. In GNU Radio Companion, we're going to have the blocks, or the sampling rate, obviously, that gives us how many, samples per second. Then we're going to ask ourselves how many samples per symbol. The samples per symbol, we set it at 30.
Then we ask GNU Radio Companion to create a random source of bits. So we say minimum 0, maximum 2. It means it will be generating zeros and ones, 1,000 of them, and then it repeats the sequence. And remember that each one of these bits, it's going to be changed into either a -1 for a 0 or a 1 for a 1. And then we want to make sure that hold on, let me move this out of my way. I can't see. Oh, here we go. This block here specifies how many samples per symbol that we saw before we're going to be implementing, right? So each symbol has a duration of, there's 30 samples per symbol divided by, here we have 10,000 samples per second. So it's 3 milliseconds for every symbol. Every symbol duration will be 3 milliseconds, and the throttle is to make sure that the computer obeys that rate. So we have the first block, generates zeros and ones, maps the zeros to -1s and the ones to ones. The interpolating FIR filter does two things. It replaces each bit with 30 samples, and it convolves the 30 samples with a raised cosine impulse response. Now, I'd like to ask you, please, I hope you have already taken the GRC code flow graph that I emailed you or that I put up in Canvas and already put it in your working directory in the lab, because the FIR filter has something like 200 taps in it. And I generated it in MATLAB and imported it into GRC. And you definitely don't want to, like, you know, input it 300 points. I mean, I did it just by importing, you know, copy pasting, but I did not send you the taps. So it would be extremely cumbersome for you to do it manually. So I want you to make sure that you have the working flow graph in your working directory in the lab. This FIR filter is going to replace each bit with 30 samples and then convolve the 30 samples with the root raised cosine impulse response. So you can see there, that's why it says interpolation 30. And then the taps are the convolution taps. The throttle enforces the sampling rate. And now we go on to the eye diagram. Now remember from lecture when we talked about the eye diagram that what you want to do is retain the transitions of older bits as we graph newer bits. So what you want to see is the transition between ones and zeros, right? And ideally, we would want hundreds of bit transitions between ones and zeros to get a proper eye diagram. Unfortunately, the GNU Radio Companion's WX GUI scope, it's no longer supported. And that does a wonderful job of just freezing the screen so that you can get many, many transitions and essentially get an eye diagram with a single block without having to implement anything difficult. However, the Qt GUI, which is currently supported, the timesync only supports up to 10 inputs. If you try to put in 11 inputs, it will not compile. So it will not create the Python code for you. So the problem is that we're going to have to do our eye diagram with only 10 snapshots, one over the other. And the way we're going to do that is we're going to do a Qt GUI timesync with 10 inputs. So the input that has no delay is the current or latest bit, which occupies 30 samples, and it's going to come in through here. The next one has 30 sample delay. In other words, it is the previous bit that also occupies 30 samples, right? It's bit number 9 in this example that occupies 30 samples. The next bit that has 60 samples delay, right? So it's 30 of, you know, of bit number 10 and 30 of bit number 9. So this is bit number 8. It also occupies 30 samples and it's delayed by 60 samples. And you can go one by one through all of these inputs until you get to the last input that is delayed by 270 samples or 9 bits coming in through here. All right. Now, what you're going to see on the screen, it's a very meager sort of eye diagram. It only has, 10 colors to it. I'm sorry about that. I did try to use the WX, but using it remotely, it really degraded the performance. It kept freezing up. And because it's not supported any longer, if you try to get support for it, like everybody just tells you to migrate to Qt. Still, you still get an idea of what it is. And specifically, you can see those transitions with the raised cosine filter. We have no intersymbol interference. And in this case, we don't have any noise in this example. And it's going to show you very clean transitions. So these points are going to be really sharp when the system transitions from one bit to the next. And when you add additive white Gaussian noise to the symbol, you're going to see that the eye diagram is going to change. And I want you to make observations, pay special attention to what changes occur, because I'm going to be asking you about it. How clean and clear are the transitions from one bit to the next? Is it very clear? Then you're going to use a root raised cosine filter instead of a raised cosine filter. You know from last time when we talked about this that it does incur intersymbol interference. And I'm going to ask, well, what happens to the transitions from one bit to the next due to the root raised cosine? Then you're going to insert a second root raised cosine. Again, this one was pre-programmed by me, and it's in the GRC file that I sent you. And it has like 200 taps also with a root raised cosine FIR filter. I didn't want to use the GRC root raised cosine because it has additional processing that I didn't want to use. I just wanted to use a plain ordinary convolution with a root raised cosine. So when you combine the two root raised cosine, the overall effect should be a raised cosine, thereby eliminating again the ISI. My question is, does it happen? How clean and clear are the transitions? And the final experiment, we will induce intersymbol interference in a different manner. What we're going to do is we're going to simulate intersymbol interference induced by a multipath channel rather than pulse shaping with the root raised cosine. So this is the root raised cosine pulse shaping filter, so it does not induce any intersymbol interference. It has a 30 sample interpolation. Here, with these two blocks, we're going to model the multipath intersymbol interference. Okay? So we're going to model it as an LTI system. And this variable here, which we call ISI, it's going to decide how strong the ISI is from the previous bit. And let's open this up to see what's inside of it. Okay, when you double click on that block, you're going to just see that the type is float to float. There's no interpolation. We don't need to add more samples. And then the taps are going to represent this impulse response. Okay. First, there's a 1. So you're multiplying the current sample by 1. That acts like an identity. And you know that in convolution, the identity for FIR filters is the Kronecker delta function, which is 0 everywhere except at the origin. And this pretty much looks very much like a Kronecker delta function because there's a 1 at the origin and everything else is 0. So for every bit, you take the current sample, multiply it by 1, all the other samples, all the other 29 samples of your bit, you multiply it by 0. And then there's one added thing, the ISI. The first bit of the the last sample of the previous bit, you're going to multiply it by 0.2 and add it to the current sample. So you're causing intersymbol interference artificially. So let's see what this would look like in the GNU Radio Companion. Let's say we have 2 consecutive bits. You have a 0 and then a 1. And let's say that you're specifically feeding this sample into the FIR filter. So this is the first sample of bit number 100, right? The output is going to be just the convolution, discrete time convolution, which is you take one of them, you put it in the summation, the other one you flip it and you slide it. So the output corresponding to n naught is going to be, according to our impulse response, 1 times n naught, 0 times n naught minus 1, 0 times n naught minus 2, 0 times n naught minus 3. There's 29 of these. 29 of these things multiplied by 0 until you get x of n naught minus 29 times 0. That's the last sample of the 100th bit, plus 0.2 times x of n naught minus 30. This fellow here belongs to the sample of the bit number 99. Okay? So this is the first sample of the previous bit. This guy over here comes in as interference to the output of the sample there. So this is how we are modeling our channel multipath intersymbol interference using an FIR filter. All right. Let's go ahead and go into our lab. I would like you please to open the GRC file that I sent to you.
So here we see the sampling rate at 10,000 hertz. We have the samples per symbol at 30 samples per symbol. The random source generates values between 0 and 1, and the chunks to symbols maps them to -1 and 1. Here is our Ray's cosine filter, which has the taps taken from MATLAB and copied into the GRC FIR filter, and the throttle keeps the sampling rate at 10,000 hertz. The Qt GUI will have 10 inputs: the current bit, the previous bit, the bit before that, and all the way down to 9 bits before, all of them at the same time. We generate the Python code and run it. And as you can see, we only have 10 bits that are being superimposed upon each other with transition, but the transition between bits is pretty clear. It's a sharp position there. Our next experiment is going to be the same thing, but with additive zero mean Gaussian noise. So we have to plug in our noise source and our adder and remove the connection between the FIR pulse shaping filter and the throttle. And now we will generate the Python code and run it. As you can see, the noise makes it extremely difficult to even notice that this is an eye diagram in the first place. So what we're going to do, we're going to change the amplitude of the noise from 0.4 to 0.2. And now we are going to regenerate the Python code, run it again. As you can see, the noise is still distorting a great deal, but at least you can see now that this is an eye diagram. In this one, the root raised cosine pulse shaping FIR filter taps were again taken from MATLAB and imported into GRC, into this interpolating FIR filter. In this case, we put the interpolation inside the RRC, and as you can see, the transition between bits are suddenly unclear. They're no longer at one specific point, making it extremely easy to distinguish between one bit and the next. Here, it becomes ambiguous. In the fourth experiment, we put 2 root raised cosine filters in series. We know that the combination of one root raised cosine followed by another root raised cosine is actually a raised cosine. The taps were once again obtained from MATLAB and imported into GRC, but the interpolation of the second one is only 1, since we don't want to, again, replace every sample with 30 samples. When we run it, we can see what we were expecting to see. A raised cosine does not have intersymbol interference, so we see the bit transitions very clearly in this eye diagram, which was what we anticipated by putting two RRCs in series with each other. In the fifth experiment, the intersymbol interference is simulated from a multipath channel, not from root raised cosine pulse shaping. So we have a regular raised cosine pulse shape with the taps obtained from MATLAB and imported into GRC. And then following that, we're going to have another interpolating filter that represents the intersymbol interference, just as we saw in the slides. There's a Kronecker delta function, essentially the 30 taps of each symbol, and then followed by one element multiplied by the ISI. In this case, the ISI is given a strength of 0.2. We generate the Python code, run it, and as you can see, once again, the clearest place to see the intersymbol interference is in the bit transitions, which become ambiguous and unclear due to the intersymbol interference from a multipath channel. We can exacerbate this by changing the value to 0.4, and you can see there that the opening becomes extremely small and the transitions between bits become extremely difficult to discern because of the ISI. In our last experiment before discussion, the case will be of raised cosine pulse shaping plus multipath ISI modeled in GRC plus additive white Gaussian noise, zero mean. So we need to find an adder and include it in the flow graph, and we also need a noise source. By default, the noise source is going to be Gaussian in GRC, but of course you can change that. We are going to also need to change the type from complex to float, and we're going to change the amplitude to 0.2. We also need to change the adder type from complex to float, and then correct the connections in the flow graph. Specifically, the noise source is going to be added to the output of the pulse shaping raised cosine filter, and then that will be fed into the throttle. We now generate the Python code and run it. As you can see, the effect of the ISI and the noise causes a collective distortion that can be observed in the graph. Here are some of the questions that we're going to address in today's discussion. How did we design the FIR filters in MATLAB, and then how did we import those taps into the GRC? How are the taps in GRC interpreted by the program? What would happen if we change the sampling rate? And what would happen if we change the samples per symbol? And how would that affect how we would observe the noise? The other question we'll address is, why did we choose the interpolation in the first FIR filter, not in the second? Here at the Masters in Telecommunications program, we strongly believe the best student experience involves hands-on labs and projects to equip our graduates to excel in the workplace.